45 kilometers of floating ice cracking apart in real time, visible from space, and scientists are calling it an obituary. That is not a metaphor dressed up for headlines. Robert Larder, a marine geophysicist with the British Antarctic Survey, has said plainly that his team has already written the obituary for the eastern ice shelf of Thwaites Glacier in West Antarctica. He said the last bit of ice shelf in front of the glacier is poised to disintegrate, that nobody knows exactly how it will break up, but that it is definitely going to go. Satellite images show fractures and rifts growing week by week, tearing the shelf away from the glacier behind it. This is not a projection for the next century. Researchers say this is very likely to happen within this year, in 2026, right now, while you are listening to this. That single fact is why the nickname Doomsday Glacier has stopped sounding like tabloid exaggeration and started sounding like an accurate description. Thwaites is not just one glacier among thousands in Antarctica. It functions as a structural pillar, a keystone holding back a much larger and more dangerous body of ice behind it. When people talk about Thwaites, they are really talking about the fate of the West Antarctic Ice Sheet, and by extension, the coastlines of nearly every populated continent on Earth. Understanding what just happened and why it matters requires stepping back to look at the mechanics of this glacier, the ocean currents attacking it from below, the human decisions that set this in motion, and the timeline scientists are now racing to nail down. Before going further, it's worth sitting with the sheer scale of what we're discussing, because numbers like Florida-sized can slide past without really registering. Thwaites Glacier is the widest glacier on Earth, a river of ice thick enough in places to bury a skyscraper several times over, grinding slowly toward the Amundsen Sea under its own immense weight. It's wide enough that a research team can spend an entire field season traveling across just one section of it. This is the glacier that a PBS NewsHour crew traveled to earlier this year to document firsthand, drilling directly into the ice alongside scientists trying to measure temperatures at depths where satellites cannot see. That expedition captured something important. This isn't abstract, remote science happening only through computer models and satellite feeds. People are physically standing on this ice in one of the most hostile environments on the planet, trying to understand it before it changes beyond recognition. Let's start with the basics, because the terminology matters here and it's often used loosely in casual conversation. Thwaites Glacier itself is a colossal river of ice, roughly the size of the state of Florida, grounded on bedrock in West Antarctica. It flows slowly but constantly downhill toward the Amundsen Sea. In front of it, where the glacier meets the ocean, there has historically been an ice shelf, a floating extension of the glacier, still attached, still made of glacial ice, but no longer resting on land. This floating shelf acts like a doorstop, or a buttress, wedged against the front of the glacier, physically resisting the seaward push of ice from behind. It doesn't stop the melting, it doesn't eliminate the underlying instability, but it slows things down. It buys time. That eastern ice shelf is the part now falling apart. Christian Wild, a geophysicist at the University of Innsbruck, described what satellite imagery is showing in blunt terms. Suddenly, large areas are just falling to pieces. This isn't a slow, centuries-long erosion happening at a pace too gradual to notice. This is active, visible disintegration happening on a timescale of months, tracked image by image as new cracks appear and old ones widen. To understand why this particular ice shelf is failing now, you have to look at what's happening underneath the ice, not just what you can see on the surface. This is where the real story lives, and it's a story about ocean physics as much as it is about ice. Deep in the Southern Ocean, several hundred meters below the surface, there's a vast reservoir of relatively warm water. It's not warm in the way a bathtub is warm. Water at this depth might sit only a couple of degrees above freezing. But when you're dealing with ice that has existed in a stable state for thousands of years, even a couple of degrees is transformative. For most of recent geological history, this warm deep water stayed largely offshore, kept away from the Antarctic continental shelf by patterns of wind and ocean circulation. Sometime in the middle of the 20th century, according to Larder and his colleagues, something changed. The delivery pattern of this water shifted. It began making its way onto the continental shelf right up to the grounding zones where glaciers like Thwaites meet the seafloor. Once that warm water reaches the base of the ice, it starts eating away at it from below, in places human eyes will never see and satellites can only infer. The mechanism driving this shift in water circulation traces back to changes in the southern hemisphere's westerly winds. Ocean circulation around Antarctica is largely wind-driven, and shifts in those wind patterns are what pull the warm, deep water up onto the shelf and toward the glaciers. Scientists are still actively researching the precise physical chain of cause and effect, but the broad picture is well established, and it connects directly to the wider pattern of human-forced climate change, reshaping atmospheric and oceanic circulation across the planet. When asked directly whether this is humans' fault, Larder didn't hedge. He said indications point clearly to human-forced climate change as the driver. New research is also revealing just how dynamic and fast-moving this underwater assault really is. Using ice-breaking research ships and an underwater robot called IceFin, scientists working with the International Thwaites Glacier Collaboration have tracked seawater intrusion happening more than 6 miles beneath the glacier itself. That's not a static pool of warm water sitting passively against the ice. Researchers have identified swirling eddies of ocean water, some of them up to 6 miles across, actively spinning and burrowing underneath the ice shelves. These eddies mix cold meltwater coming off the ice with warmer, saltier ocean water in a feedback loop that appears to accelerate melting rather than dampen it. And crucially, this process can be tracked changing not just year to year, but hour to hour and day to day. The glacier's foundation is being reworked on a timescale that matches weather, not geology. The IceFin robot itself deserves a moment of explanation because the engineering challenge behind it is almost as remarkable as what it has found. It's a slender, torpedo-shaped vehicle designed to be lowered through a borehole drilled straight through several hundred meters of solid ice, then released to swim freely in the ocean cavity beneath the glacier, an environment completely dark, under immense pressure and inaccessible by any other means. Once beneath the ice, it measures temperature, salinity, current speed, and direction, essentially mapping the invisible plumbing system through which warm water reaches the glacier's most vulnerable points. What it has found reinforces the eddy-driven picture researchers are now piecing together. Rather than a uniform, gradual warming spread evenly across the base of the ice shelf. The reality is patchy, turbulent, and dynamic, with pulses of warm water finding specific pathways toward the grounding zone. That kind of detail matters enormously for modeling, because a glacier being attacked unevenly in concentrated zones behaves very differently than one melting uniformly from below, and it helps explain why certain sections of the ice shelf, like the eastern portion now disintegrating, can destabilize well ahead of other parts of the same system. Layered on top of that oceanic assault is a structural story happening within the ice itself. A team of researchers from the University of Manitoba analyzed 2 decades of satellite imagery from 2002 to 2022, tracking the growth of fractures around what's known as a shear zone upstream of the ice shelf's pinning point. A pinning point, for context, is a place where an ice shelf makes contact with an underwater rise or ridge, anchoring it and providing extra stability, similar to how a tent stake holds fabric in place. Over those 20 years, the researchers found that the shelf experienced progressive fracturing around this shear zone, steadily compromising its structural integrity. The total length of fractures across the shelf grew from around 100 miles to over 200 miles in just 2 decades. Interestingly, the average length of individual fractures actually decreased over that period, even as the total fracture length more than doubled. That combination, more fractures, but each one shorter, points to new and different kinds of stress acting on the ice. A sign that the shelf isn't just cracking in the same old ways more often. It's cracking in new ways it wasn't cracking before. Put those two forces together, warm water eating the ice from below, and structural fracturing spreading across the shelf from within, and you get a picture of a support structure failing on 2 fronts simultaneously. That's what's driving the confidence behind statements like the one from Larder about writing this ice shelf's obituary. Now here's the part that requires some careful distinction because it's easy to blur 2 very different things when talking about this story: the loss of the ice shelf and the collapse of the glacier itself. These are not the same event, and conflating them either overstates or understates the danger, depending on how you frame it. Losing the eastern ice shelf does not mean Thwaites Glacier is about to collapse next year, or even within the next few decades. Larder has been explicit about this. A glacier this large, roughly the size of Florida, takes centuries to fully disintegrate, and scientists still struggle to model precisely how that long process will unfold. Nobody serious is claiming the glacier itself vanishes on any kind of short timeline. What the loss of the ice shelf means is narrower, but still serious. One of the primary mechanisms slowing the glacier's flow toward the ocean is about to be removed. The glacier has been retreating with a brake applied. That brake is about to come off. Scientists have already observed early signs of what happens once that resistance weakens. Over the last several years, as the ice shelf's internal structure has grown more fragile, researchers have documented an area of grounded ice where glacier ice flows into the ice shelf, beginning to move faster. That acceleration is direct evidence that the ice shelf really was doing something to hold back the flow of ice behind it. Once the shelf is gone entirely, researchers expect to see more of this. Increased flow speed, increased calving, and a faster overall rate of ice discharge into the ocean. Larder described it as something that will be quite a spectacular event to watch unfold in satellite image sequences. And then, in his words, it's going to be very interesting to see how the glacier responds to that. That's scientific understatement for something that will likely reshape sea level projections for the rest of this century. So how much ice are we actually talking about? And what does it mean in terms of sea level, expressed in real numbers rather than vague dread? If Thwaites Glacier were to fully collapse, eventually, over a time scale of centuries, it would raise global sea levels by roughly 26 inches, or 65 centimeters. That number alone is why coastal engineers and city planners pay close attention to what happens in this remote corner of West Antarctica, thousands of miles from the nearest major population center. But Thwaites doesn't exist in isolation. It functions as a keystone for a much larger, deeply unstable region of the ice sheet around it. Larder's assessment is sobering on this point. The loss of Thwaites likely destabilizes other marine-based portions of the West Antarctic Ice Sheet, because the underlying problem, the reason this whole region is so vulnerable in the first place, is that virtually the entire glacier and its neighbors sit on bedrock that lies well below sea level. When ice sheets are grounded below sea level like this, warm ocean water can attack them from underneath in a way that simply isn't possible for ice sitting on bedrock above the waterline. It creates a feedback loop of instability that, once triggered, becomes very difficult to reverse. Because of that broader instability, Larder and his colleagues estimate the West Antarctic Ice Sheet carries a total commitment of more than 3 meters, nearly 10 feet, of eventual global sea level rise, once Thwaites and its structurally connected neighbors are factored in. Read that again. Not 65 centimeters, 3 meters, 10 feet. That is the scale of what's genuinely at stake if this instability plays out to its logical conclusion, which most researchers now consider likely, even if the exact timeline remains one of the biggest open questions in glaciology. And that timeline question is worth sitting with because it's where honest scientific communication gets genuinely difficult. Right now, the global rate of sea level rise from all sources combined sits around 4 to 4.5 millimeters per year. Say that number out loud to someone outside the field, and it's almost impossible to make it sound alarming. A few millimeters. You could barely see that difference on a ruler. Larder himself acknowledged this communication problem directly. It's difficult to get people excited about adding an extra millimeter to that number. But he also explained why that framing misses the point entirely. Small increases in baseline sea level produce wildly disproportionate increases in flooding risk when you look forward a decade or two. You don't need a meter or two of sea level rise to transform a once-a-century coastal flooding event into a once-a-decade event, or even an annual one. Small, steady increases in the baseline water level shift the entire statistical distribution of storm surge and high tide flooding upward, turning rare disasters into routine occurrences. Coastal cities from New York to Miami to San Francisco to Boston are already grappling with this shifted baseline, and infrastructure decisions being made in those cities right now depend heavily on how fast Antarctica's contribution accelerates. One recent study modeling Thwaites' future ice loss projected the glacier could be shedding somewhere between 180 and 200 billion tons of ice per year by 2067. That's a 4-decade horizon, well within the lifetime of people alive today, and it represents a substantial acceleration from current rates. Losing that much mass annually would meaningfully accelerate global sea level rise well before the glacier itself is anywhere close to fully disappearing. This is the mechanism by which a glacier that takes centuries to vanish entirely can still produce dangerous, disruptive sea level rise on a timescale of decades. You don't need total collapse to get significant impact. You just need the rate of loss to keep climbing year after year, as buttressing structures like the eastern ice shelf disappear one by one. It's also worth understanding why scientists remain unable to give a precise date for when any of this fully plays out, because that uncertainty itself is scientifically meaningful rather than a dodge. There's a whole range of ice sheet computer models currently in use across the research community, and they produce a range of predictions rather than a single number, modeling how a body of ice the size of Florida will interact with warming, circulating ocean water over the coming decades and centuries involves enormous physical complexity. The shape of the bedrock underneath, the exact pathways warm water takes as it circulates beneath the ice, the rate and pattern of new fracturing, the way calved icebergs interact with the remaining shelf, and feedback loops that aren't yet fully characterized. Larder was candid about this limitation. Nobody can state with very high confidence what the rate of ice loss will be over the next century or two. That's not scientists being evasive. That's an honest acknowledgement that predicting the precise behavior of one of the most complex physical systems on the planet, involving glaciology, oceanography, and atmospheric science all at once, is genuinely difficult, even with decades of dedicated research and increasingly sophisticated satellite monitoring. What has changed, and what justifies calling this a new warning rather than just more of the same slow-moving climate story, is the shift from long-range projection to near-term observable event. For years, discussions of Thwaites centered on multi-decade or multi-century modeling exercises, abstract numbers derived from computer simulations. What's different now is that scientists are pointing at a specific physical event, the breakup of a 45-kilometer ice shelf happening this year, tracked in real time through a sequence of satellite images anyone can look at. Robert Larder said his team has already written that ice shelf's obituary. That's not language you use for something that might happen sometime in the next 50 years under certain modeled conditions. That's language you use for something that is actively happening right now, visible in the data, with fractures and rifts you can watch grow week over week. This also connects to a broader pattern researchers are now documenting across the wider Antarctic system, not just at Thwaites specifically. A study published in the journal Science Advances earlier this year examined what researchers describe as compound drivers of Antarctic sea ice loss and what they call Southern Ocean destratification. In plain terms, the ocean layers around Antarctica, which have historically kept warm water trapped safely at depth, are undergoing a fundamental structural shift. Heat that used to stay locked away hundreds of meters down is increasingly making its way toward the surface, where it becomes available to melt sea ice directly, in addition to attacking glaciers like Thwaites from below at the grounding line. This suggests the mechanisms threatening Thwaites aren't an isolated, localized phenomenon confined to one glacier in one corner of West Antarctica. They appear to be part of a larger reorganization of ocean circulation and heat distribution happening across the entire Southern Ocean system, which raises the stakes considerably beyond just this one glacier's fate. It's worth pausing here to address the obvious question a skeptical listener might raise. Haven't scientists been predicting Thwaites' collapse for years already? Isn't this just the same warning recycled with a new headline? The honest answer is nuanced. Concern about Thwaites is not new. The International Thwaites Glacier Collaboration, the joint research effort between American and British scientific agencies that Larder helps coordinate, was established back in 2018, specifically because earlier research had flagged Thwaites as a critical, poorly understood piece of the West Antarctic puzzle. Researchers have been drilling into the ice, deploying underwater robots, and gathering satellite data for close to 8 years now, continuously refining their understanding of how the system behaves. What's different about the current moment isn't that concern about Thwaites suddenly appeared out of nowhere. What's different is that a specific, previously stable structural feature, the eastern ice shelf, has now crossed an observable threshold and entered active disintegration, something researchers can point to concretely rather than project abstractly. Larder's own framing captures this evolution well. Initially, when the Doomsday Glacier nickname first attached itself to this research effort, scientists actively resisted using it, because they felt it prejudged conclusions their research hadn't yet established. Now, after 8 years of accumulated results, Larder says he increasingly thinks the nickname is appropriate. That's a meaningful shift in scientific confidence, arrived at gradually through mounting evidence rather than a single dramatic revelation. There's also a specific reason drilling expeditions have continued, even as satellite monitoring has improved dramatically. Satellites are excellent at tracking surface features, crack propagation, ice shelf area, calving events, and overall glacier velocity measured through repeated imaging passes. But some of the most critical physical processes happen at the interface between ice and ocean, hundreds of meters beneath the surface, where satellites simply cannot see. That's why research teams have physically traveled to one of the most remote, hostile environments on the planet, drilling boreholes directly through hundreds of meters of ice to measure temperature, salinity, and current patterns at the grounding line itself, and to deploy instruments like the IceFin robot directly into the water beneath the ice shelf. This is genuinely difficult, expensive, logistically punishing science, conducted in a place where a support vessel might spend weeks working through sea ice just to reach a research site, and where a field season is measured against a brutally narrow window of Antarctic summer weather. The fact that researchers keep returning year after year, funding cycle after funding cycle, tells you something about how seriously the scientific community treats the stakes involved. So what actually happens next, in practical terms, once this eastern ice shelf finishes breaking apart? Based on what researchers are telling us now, expect several things to unfold in sequence. First, continued fragmentation visible through routine satellite monitoring, likely producing large icebergs calving away from what remains of the shelf, image by image, over the coming months. Second, an acceleration in the flow speed of the grounded glacier ice behind where the shelf used to be, similar to, but likely more pronounced than, the acceleration already observed in recent years as the shelf weakened. Third, closer scientific attention to how the newly exposed glacier front behaves once it's directly exposed to open ocean water and wave action, without a floating shelf in front of it to dampen and buffer that interaction. And fourth, continued refinement of ice sheet models as researchers incorporate this real-world event into their projections, potentially tightening the range of predictions for how quickly Thwaites and the broader West Antarctic ice sheet behind it will contribute to global sea level rise over the coming decades. None of this means catastrophe arrives next year, or even within the next decade. It means a critical piece of a much larger, slow-moving, and largely irreversible process has now visibly shifted from a stable to an unstable state, adding urgency to research efforts and, ideally, to the policy conversations that depend on accurate, current scientific information. Larder was direct about the scale of commitment involved even under optimistic emission scenarios. Even if the world reaches net zero emissions by 2050, an ambitious target that current policy trends aren't on track to meet, Thwaites Glacier is still going to go. The 65 centimeters of sea level rise associated with its eventual loss is already locked in, a commitment made by decades of past emissions rather than something future policy can now undo. That's a difficult, uncomfortable thing to communicate honestly, and it's precisely why researchers like Larder continue emphasizing it rather than softening the message for easier consumption. That framing matters enormously because it reshapes the conversation from "can we stop this?" to "how do we prepare for what's already coming?" while still working to prevent the situation from getting meaningfully worse. Reducing emissions going forward doesn't erase the sea level rise already baked into the system by ice already destabilized. What it can do is limit how much additional ice becomes destabilized beyond what's already committed, particularly across the wider West Antarctic Ice Sheet, where that estimated 3-meter total commitment represents a range of possible outcomes, depending heavily on how much warming the planet experiences in the coming decades. The difference between a world that stabilizes warming soon and one that continues on a higher emissions trajectory could very plausibly be the difference between losing Thwaites alone and losing much of the interconnected West Antarctic system around it. It's also worth naming specifically which places carry the most exposure, because coastal flooding can otherwise sound like a diffuse, distant problem. Researchers studying U.S. flood risk have already flagged cities including New York, Boston, San Francisco, and Miami as facing major escalating risk from rising baseline sea levels, with millions of residents potentially exposed to extreme flood damage as the century progresses. Some studies looking specifically at U.S. coastal geography have identified dozens of cities, more than 30 in one analysis, that are simultaneously dealing with rising seas and sinking land, a combination that compounds the danger far beyond what ocean-driven sea level rise alone would produce. None of those cities are anywhere near Antarctica. That's precisely the point. Ice loss at Thwaites doesn't stay a local Antarctic story. Through the basic physics of gravity and ocean redistribution, mass lost from West Antarctic ice sheets spreads unevenly around the globe, and it shows up as measurable flood risk in the drainage systems, subway tunnels, and building foundations of major cities a hemisphere away. There's a scientific culture element worth mentioning too, because it shapes how much weight to put on a statement like Larder's. Researchers working within an active, ongoing international collaboration, like the ITGC, tend to be cautious by professional habit, wary of overstating findings, wary of feeding a media narrative that outruns the underlying data. That caution is exactly why it matters when a scientist embedded in that culture, someone who explicitly says his team initially resisted the Doomsday Glacier nickname because it prejudged their conclusions, arrives at a point where he says the name now fits. That's not a marketing decision. That's a researcher updating a professional judgment after 8 years of first-hand data collection. Boots on the ice, boreholes drilled, robots deployed, satellite archives analyzed frame by frame. When the people closest to the evidence become more convinced rather than less, that shift deserves attention independent of how any single headline chooses to frame it. For coastal communities, the practical takeaway from all of this isn't panic about an imminent flood next year. It's about planning horizons. Infrastructure built today, particularly major coastal infrastructure like seawalls, drainage systems, port facilities, and building codes for flood-prone zones, typically needs to function for 50 to 100 years or more. Decisions being made right now about that infrastructure need to account for a sea level trajectory that includes meaningful contributions from West Antarctic ice loss, not just the more predictable thermal expansion of warming ocean water or the melting of mountain glaciers, both of which are easier to model with tighter uncertainty bounds. Antarctica represents the biggest wild card in global sea level projections, precisely because ice sheet dynamics, the physical process of ice actually breaking apart and flowing into the ocean rather than simply melting in place, remain the least well understood and most difficult to model piece of the puzzle. Robert Hunziker, writing about this same research, described Thwaites as the wild card of all wild cards, with enough mass to genuinely spook the world if it behaves in ways current models haven't anticipated. Given how consistently Thwaites has outpaced earlier predictions over the past decade, retreating faster than models from just a few years ago suggested it would, that wildcard framing looks increasingly justified rather than alarmist. It's also worth noting what this story reveals about the pace of climate research itself and how findings evolve as monitoring technology improves. A decade ago, scientists couldn't track fracture evolution, ice shelf thinning, and detachment risk in anything close to real time. Today, researchers can watch a 45-kilometer ice shelf's structural collapse unfold through sequences of high-resolution satellite images updated regularly, essentially watching a slow-motion disaster develop with a level of detail that simply wasn't available even 5 or 10 years ago. That improved visibility is precisely why scientists can now speak with more specificity and more confidence about what's happening this year, rather than only being able to describe multi-decade trends in vague, hedged language. It's a reminder that climate risk often advances through thresholds and discrete events rather than smooth, easily digestible trend lines. One year's headline about an ice shelf breaking up isn't necessarily the final disaster. It's the loss of another stabilizing feature that shifts the underlying baseline for whatever change comes next, moving the entire system one step further from the relatively stable state it occupied for thousands of years before industrial era warming began. So, where does that leave us? Antarctica's Thwaites Glacier is not collapsing tomorrow. It's not going to swallow coastal cities next year, or even within most of our lifetimes in the dramatic, sudden-way disaster films sometimes portray. But the protective ice shelf that has been slowing its retreat for as long as scientists have studied it is now actively disintegrating, tracked in real satellite images, described by the scientists studying it as something they've effectively already written the obituary for. That loss removes one of the last natural breaks on a glacier that, by itself, carries a commitment of 26 inches of eventual global sea level rise, and which sits at the center of a broader West Antarctic system carrying a commitment of more than 3 meters. The ocean water driving this destruction traces back, according to the researchers who've spent nearly a decade studying it directly, to human-forced changes in wind patterns and ocean circulation. And the timeline for how fast all of this unfolds remains genuinely, honestly uncertain, dependent on emissions, decisions being made in the present, even as the researchers on the ground and beneath the ice increasingly agree on one thing. Whatever else remains uncertain about Thwaites Glacier, the direction of travel is not. What happens over the next several months will be worth watching closely, not because any single satellite pass will resolve the bigger questions, but because this is one of those rare moments in Earth science where a slow, abstract process becomes something concrete and observable within a normal human attention span. Most climate change unfolds too gradually for any one person to watch it happen. A degree of warming here, a few millimeters of sea level rise there, spread across years and decades in ways that resist direct perception. The breakup of a 45-kilometer ice shelf is different. It's a visible, trackable, datable event, unfolding on the same kind of timescale as a news cycle rather than a geological epoch. For scientists, that offers a rare opportunity to validate models against real-world behavior in close to real time. For everyone else, it offers something almost as valuable. A chance to actually witness one link in the chain connecting global emissions to local flood risk, rather than simply being asked to trust a projection decades removed from any lived experience. The ice shelf in front of Thwaites Glacier is, by every account from the people who study it most closely, already gone in every sense but the physical one. What happens next depends on how the rest of the system responds, and on how seriously the observable present is treated as a guide to the uncertain future still being written.